flat, indicating that there is no further net heat transfer in the axial direction. This often occurs when the fluid has reached thermal equilibrium with its surroundings or when axial conduction becomes negligible compared to the bulk flow of heat. This is a type of zero gradient boundary condition. In total, we have six boundary conditions. This is precisely the number of conditions required to solve our system of three second order differential equations. As each second order equations yields two constant of integration, resulting in a total of six unknowns that need to be determined. Now let's delve deeper into the process of how we actually utilize these boundary conditions to obtain the specific solution for the temperature profile in each of the three zones. The general methodology involves a series of interconnected steps. Here, first step is to obtain the general solution for each zone's differential equation. For each of three zones, we first need to find the general solution to the corresponding second order linear ordinary differential equation. The form of these general solutions will depend on the characteristics of each equation, particularly the presence and the nature of source term as in zone 2. For the homogeneous equations in zone 1 and zone 3, where s equals to 0, the general solutions will typically involve linear combination of exponential functions. The characteristic equation of these second order linear homogeneous differential equations will have two roots, let's say lambda 1 and lambda 2. The general solution will then be of the form t of z is equals to c1 e to the power lambda 1 into z, where c1 and c2 are the constants of integration that we need to determine. The nature of these roots are real and distinct, real and repeated or complex conjugators, and the nature of these roots will dictate the exact form of the exponential terms. For the non-homogeneous equation in zone 2 where s is not equals to 0, the general solution will consist of two parts, the complementary solution and the particular solution. The complementary solution, which means the general solution to the homogeneous equation obtained by setting set equals s equals to 0, and the particular solution, which means any specific function that satisfies the non-homogeneous equation. Now, the form of the particular solution depends on the form of the source term s. If s is a constant, we might guess a constant particular solution. If s is a function of z, we might need to use techniques like the method of undetermined coefficients or variations of parameters to find the particular solution. The general solution for zone 2 will then be t of z is equals to a1 e to the power mu 1 z plus a2 e to the power mu 2 into z plus t of z, where a1 and a2 are the constants of integration and t of z is a particular solution. And in step 2, apply the boundary conditions to form a system of algebraic equations. Once we have the general solutions for each zone, the next crucial step is to apply the six boundary conditions we have defined. Each boundary condition will provide a relationship between the temperature and or its derivative at a specific location, allowing us to form a system of six algebraic equations involving our six unknown constant of integration. The temperature continuity conditions at z equals to 0 and z equals to L, which are boundary condition 2 and boundary condition 4, will provide two equations by equating the expression for temperature from the adjacent zones at these interfaces. Now, the heat flux continuity conditions at z equals to 0 and z equals to L, where boundary condition 3 and boundary condition 5, which involve the first derivative of the temperature profile and the effective thermal conductivities, will provide another two equations. We will need to differentiate our general solution with respect to z to apply these conditions. The inlet condition as z approaches negative infinity, which is boundary condition 1, will impose a constraint on the solution for zone 1. For example, if one of the exponential terms in the general solution for zone 1 grows unbounded as z tends to minus infinity, its coefficient must be 0. to satisfy this boundary condition, thus helping to determine one of the constants. Similarly, the outlet condition for zero temperature gradient as z approaches positive infinity, which is boundary condition 6, will impose a constraint on the solution for zone 3, often forcing one of the coefficients of the exponential terms to be 0 to prevent the temperature from growing indefinitely or having a non-physical gradient far downstream. And the third step is to solve the system of algebraic equations for the constant of integration. After applying all six boundary conditions, we will have a system of six simultaneous algebraic equations with six unknowns. Solving this system is often the most mathematically intensive part of the problem. The complexity of this step will depend on the form of the general solutions and the boundary conditions. Techniques such as substitutions, elimination, or matrix methods can be used to find the values of these constants. And the final step is substitute the determined constants back into the general solution. Once we have successfully solved the system of algebraic equations and obtained the numerical all or symbolic values of all six constants of integration, the final step is to substitute these values back into the general solution we found in step 1 for each of three zones. This will yield the unique temperature profile, which is T of Z, for each zone that satisfies both the original differential equation within that zone and all the imposed boundary conditions at the interfaces and the ends of the reactor. This final set of equations provide provides a complete mathematical description of the temperature distribution along the axial length of our tubular fixed bed reactor. Here we are having visual representation of the resulting dimensionless temperature profile for a specific, though unspecified in detail in these concepts. Choice of the source function and after the application of the boundary conditions. This figure plots a dimensionless temperature, often defined as theta, or a similar normalized form as a function of the dimensionless axial coordinate z by L. The presentation of the solid temperature profiles after applying the boundary conditions emphatically highlights their indispensable role. Without these boundary conditions, we would be left with merely the general forms of the solutions containing undetermined constants and offering no specific insight into the temperature distribution within our reactor under a given set of operating conditions. The boundary conditions act as filters, selecting the one physically realistic solution from an infinite family of mathematical possibilities. To summarize our discussion, the formulation and application of boundary conditions are fundamental to solving heat transfer problems and indeed a vast array of other transport phenomena that are described by differential equations. They serve as a crucial link between the abstract mathematical representation and the concrete physical reality of the system we are studying. In this specific context of our tubular fixed bed reactor with a chemical heat source, the physical and geometric configuration of the system, specifically the presence of distinct zones with different properties and the existence of interfaces between them, directly dictates where we need to impose boundary conditions. We need conditions at the system boundaries and at the internal interfaces between the different packed sections and fundamental physical principles such as the conservation of energy and the requirement for continuous physical properties like temperature in the absence of phase changes or other discontinuities provide the mathematical form and justification for these boundary conditions. Additionally, the specification of inlet conditions is essential for defining the initial state of the system. The process of solving the differential equations for each zone is inherently coupled with the application of these boundary conditions. The general solutions obtained from the differential equation contain unknown constants, and it is the application of the boundary conditions that generates a system of algebraic equations that allow us to determine these constants, thereby yielding the unique and physically relevant temperature profile throughout the reactor. And now I think it's worth briefly expanding on a couple of key parameters that significantly influence the temperature profile and the role of boundary conditions, such as effective thermal conductivity and chemical heat source term, which is S. The chemical heat source term S in zone 2 is also paramount importance. As mentioned earlier, it represents the rate of heat generation for exothermic reactions or consumption for endothermic reactions per unit volume of the reactor due to chemical reaction taking place on the catalyst surfaces. The functional form of S is typically derived from the kinetics of the reaction and will generally depend on temperature and the concentration of the reacting species. For instance, according to the Arrhenius equation, reaction rates and hence the heat generated or consumed often have a strong exponential dependence on temperature. Therefore, the differential equation in zone 2 can be non-linear if S is a function of T, making it more challenging to solve analytically and potentially requiring numerical methods. While our experts don't provide a specific form for S, it's crucial to remember that its nature profoundly impacts the temperature profile and the effectiveness of the boundary conditions in the yielding a physical meaningful solution. In conclusion, the interplay between the governing differential equations and the meticulously defined boundary conditions is what allows us to move from a general mathematical description of heat transfer in our tubular fixed bed reactor to a specific and predictive model of temperature distribution. Understanding these concepts is not just an academic exercise, it's a fundamental to the design, analysis, and a safe and efficient operation of chemical reactors and many other engineering systems involving transport phenomena. And the boundary conditions encapsulate the essential physical constraints of our system, ensuring that the mathematical solution we obtain truly reflect the behavior of the real world process. Thank you for joining. And now we will proceed with the graph explanation by Akanksha.
Now we'll, now we'll explore a well-known temperature distribution model which assumes negligible axial diffusion and where heat is produced in a central zone, giving us insights into how temperature evolves within the reactor. This system is a representative of many industrial catalytic reactors, such as those used in ammonia synthesis, methanol production, or even regenerative thermal oxidizers. Let's break down the physical system first. We have a fixed bed reactor, meaning the catalyst remains stationary and the fluid flows through it. The flow is axial and the temperature is tracked along the length of the reactor. The reactor is conceptually divided into three zones. Zone 1, pre-reaction zone. Zone 2, reaction zone, where heat is generated. Zone 3, post-reaction or stabilization zone. These are shown in the dimensionless graph. The x-axis is the dimensionless length. Capital Z is equal to small z divided by capital L, and the y-axis is the dimensionless temperature. Theta is equal to T minus T naught divided by Tf minus T naught. This dimensionless approach makes the model scalable and general. Now we'll look at the mathematical modeling. The governing principle here is the energy balance, simplified to a first order differential equation because actual conduction is assumed negligible. The general form of energy balance in zone 2 is d theta upon dz is equal to n theta, where theta is dimensionless temperature, z is the actual coordinate, n is a dimensionless heat generation parameter. It incorporates the reaction rate and heat release. This equation is separable and easy to solve. Theta z is equal to e to the power nz. This solution describes how temperature changes exponentially in the reaction zone. Let's now explore what each zone represents in terms of both physics and mathematics. Now we'll go zone by zone. Zone 1 is a preheating or pre-cooling zone where no reaction is occurring. The fluid is preconditioned before entering the reactor. The temperature is uniform and constant. Theta 1 is 1. And when we move on to the next zone, which is the reaction zone, the heart of the system, heat is generated due to chemical reaction. The heat source is modeled as f of theta is equal to theta. This is the simplified function which we are considering, and then we have different values of n which produce different behaviors. N is equal to 2 is rapid temperature rise, which shows it is a strongly exothermic reaction. N is equal to 1 shows that there is a moderate rise. N is equal to minus 1 shows it is cooling and endothermic. N is equal to minus 2 shows that it is strongly endothermic. The temperature drops sharply. This zone is especially important for safety. High N can lead to hotspots, which might damage catalysts or cause runaway reactions. Zone 3 is the post reaction zone. After the reaction completes, no more heat is produced. The temperature stabilizes at the value from the end of zone 2. Theta 3 is equal to theta 2 at z is equal to 1. Now we'll discuss about the implications in the reactor design. This model, while simplified, teaches us a lot about how to design reactors. Thermal runaway. For high N, temperature rises exponentially. We need to control feed rates, use diluents, or introduce cooling to prevent danger. Catalyst safety. Exceeding safe temperature limits can deactivate or sinter the catalyst. Process control. Knowing where the temperature peaks helps place thermocouples or control valves efficiently. Engineers might even intentionally design Zone 1 to absorb heat from Zone 2, a concept known as heat integration. Also note that this model neglects axial conduction. In real systems with metal reactors or high thermal conductivity, axial heat spreading can flatten the profile. Now, to summarize, this plot represents a dimensionless temperature profile in a composite medium with internal heat generation. The exponential form of theta 2 is equal to e to the power nz gives insight into how quickly temperature can rise or fall based on the reaction's thermal nature. Even with simplified assumptions, it provides valuable design insights that can be built upon for more advanced models involving conduction, radial gradients, and reaction kinetics. Understanding this helps engineers predict, prevent, and optimize whether it's for safe reactor operation, energy efficiency, or product quality.
Here we have few key features that are continuity of temperature. Observe how the different curves representing the temperature in zone 1, zone 2 and zone 3 smoothly connect at the interfaces that are z by L equals to 0 and z by L equals to 1. This visual conformation aligns with our boundary conditions that explicitly require the temperature to be continuous at these points. And the other key feature is to the discontinuity of slope, that is heat flux. While the temperature is continuous, you can see that the slope of the temperature profile, which is proportional to the heat flux, according to the Fourier's law, changes at the interfaces. This change in slope is consistent with the continuity of a heat flux boundary condition and arises due to the potential differences in the effective thermal conductivities between the inert and catalytic zones. Where the effective thermal conductivity is higher for a given heat flux, the temperature gradient will be smaller and vice versa. And now the impact of parameter n. The figure shows multiple curves, each labeled with a different value of n. It's highly likely that n represents a dimensionless parameter that is related to the magnitude of the heat generation rate due to the chemical reaction, or perhaps a ratio of the heat generation rate to the rate of heat transfer. By comparing the curves for different values of n, we can gain a qualitative understanding of how the intensity of the chemical reaction affects the temperature profile. For instance, a higher positive value of N generally leads to a higher peak temperature within the catalytic zone, indicating which is zone 2, indicating that more heat is being generated that can be effectively removed by convection or conduction. Conversely, negative values of N might represent an endothermic reaction leading to a temperature drop in zone 2. And one more basic key feature is profile in inert zones. In zone 1, that is Z by L less than 0, and zone 3, which is Z by L greater than 1, where no net heat generation from the primary reaction occurs, the temperature profiles tend to approach asymptotic values or exhibit a more gradual change, reflecting the balance between convective and conductive heat transfer in the absence of significant source or sink. The behavior in these zones is heavily influenced by the conditions at the interfaces within the reaction zone. The presentation of the solid temperature profiles after applying the boundary conditions emphatically highlights their indispensable role. Without these boundary conditions, we would be left with merely the general forms of the solutions containing undetermined constants and offering no specific insight into the temperature distribution within our reactor under a given set of operating conditions. The bound possibilities. This exploration of chemical heat sources in fixed bed reactors provides a foundational understanding for more advanced topics in reactor design and process control. Managing heat effectively is crucial for reactor safety, product selectivity, and overall process efficiency.
Well, that brings us to the end of our discussion today. We hope you found this deep dive into chemical heat sources insightful. Thank you for tuning into Chemical Engineering Insights.
Thank you everyone. Until next time, keep exploring the fascinating world of chemical engineering.